everybody. Reporting to you again from the Glamour City, Hollywood.
There are a lot of airports in the country, and they're in very rural areas. They can serve a lot of needs, but they're very basic in terms of, say, their landing navigation infrastructure. Most of them are untowered, or maybe they have a tower, if you're lucky, that operates just during the day, not at night. Radar coverage, other traffic awareness type technologies on the ground as well could be limited. It really highlights when a pilot steps into an airplane and flies into one of these smaller airports, how much a human brings on board the airplane in terms of its ability to navigate and operate in and out of those terminal areas. That lack of infrastructure and combined with, say, need for operating in all types of weather conditions is a big challenge, and probably a reason why those airports are underutilized, aside from recreational flight and a few smaller outfits.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Dr. Eric Muir, founder of Volair. Welcome to the show today.
Yeah, thanks for having me, Scott.
So you have a PhD from the University of Michigan's Aerospace Department and have led autonomous flight technology development at Boeing. I wonder if you could tell us a little bit more about your career and your experience.
Yeah, sure thing. When I started my, education at the University of Michigan, certainly didn't even have exposure to some of the exciting topics in aerospace, particularly in the advanced aerial mobility sector, autonomous flight, a lot of things that my career has segued into. But that said, there were kind of some foundational building blocks that I started with there that I think have led me here. First of all, always had a fascination with aircraft, got my pilot's license when I was in graduate school, and was actually working on a project looking at the effects of ingesting a bird into a jet engine that were motivated by the so-called Miracle on the Hudson landing. We've probably all seen the movie Sully, and if you kind of fast forward that into my career at Boeing, working on the jet engines for the 777, there was always kind of in my mind of how do I push the envelope in aerospace and also couple my interest in the mathematics and mechanics of aerospace engineering with this very human-centric aspect of the aerospace field, which is piloting. And so that exposure to that Miracle on the Hudson was, very kind of motivating for me. And I was just very fortunate to be able to get an opportunity to work in autonomous flight at Boeing, which has kind of then led me all the way through to the founding of Volair, which is applying a lot of cutting edge technologies, whether that's on the perception side, decision-making side, to really do what's, to me, very centric to aviation and aerospace, the piloting role in developing technologies to make that more efficient, safer, and more scalable.
So we're going to come back to this notion of piloting in just a few minutes, and that's an important topic. There's another thing that you may have mentioned in your notes, which is the Rotorcraft noise reduction. I wonder if you could share us a little bit about that.
Yeah, absolutely. I did some work in when I was doing my master's research for my master's degree on noise reduction technologies for rotorcraft. At the time, the applications were not the electric eVTOL aircraft that we see all over the LinkedIn news feeds and investor news and things like that. But instead, they were applied to traditional helicopters, trying to make helicopters quieter, primarily for military applications. It's kind of ironic because at the time, I was looking at a very challenging problem of rotorcraft noise reduction applied to 50-year-old type of aircraft, being helicopters, with really no foresight to how relevant that type of research and that type of technology would be to the advanced aerial mobility market of today, and in making these eVTOL aircraft quiet so that the public has a little more comfort and willingness to allow these aircraft to be operating in our urban environments.
Yeah, I think that's a fantastic point, and it's interesting in terms of the foresight, right? Because certainly traditional helicopters are incredibly noisy, and of course the force that they create as well. Some of the things that we've even heard in terms of not just autonomous flying vehicles, but in terms of even drones and drone delivery is exactly around those noise factors as well. Now, going back to your experience at Boeing, I know you worked on autonomous systems development as a manager there. I wonder, in that context, what were some of the opportunities that you saw that perhaps maybe the market wasn't quite addressing at that point?
Yeah, absolutely. When we started working on this technology space probably middle of 2016 or so, there were not the advancements we've seen outside of the large OEMs. So this was really a fresh new area, and it was exciting because we got to explore, at least go through the mental exercise of a whole lot of different areas. But I think what's first of all key is understanding and appreciating the technology that already exists, the level of automation, and also the high level of safety that the aviation community has already been able to achieve with our commercial travel and things like that. But I think what was observed and what was missing is that most of the aviation travel, whether it's for movement of people or movement of goods, are leveraging less than 100 airports nationally at a high level. We have probably 25,000 or so airports across North America. Many of them are smaller, untowered, and very underutilized. And so what we saw an opportunity as we were looking at this autonomous flight problem is, how can you put technology on board the aircraft, even if it was still piloted, that can kind of expand that operational envelope and be able to leverage those regional airports? And then how can that segue into an operational mode where you have a remote pilot at a ground station infrastructure managing a fleet of aircraft and kind of segueing the technology into fully autonomous? So I think that was kind of a key observation. I think that the second thing is, same time that we were doing this work, the autonomous driving industry was really booming. Lots of new technologies coming out, different AI technologies, computer vision technologies, sensor technologies, LiDAR. All these things were maturing very rapidly for the ground autonomy use case. And we were aware that not all of these technologies would make their way onto an airplane or even made sense. But it was, doing due diligence to go through and look at these and understand, why don't aircraft have, sensing systems like we have on our cars that you purchased today, ADAS, lane keeping, traffic alert, things like that, or what are the parallels to that industry that could also be leveraged just from a situational awareness standpoint for human pilots, and again, can mature to segue into more highly automated and fully autonomous technology capabilities.
Well, thank you for sharing. And I think back then, and again, several years, but in those several years, a lot has advanced, of course. But you're talking about underutilized regional airports. And of course, there's a lot of limitations and challenges. And what you're talking about is really a whole new sort of ecosystem and capabilities that does not exist. And it's hard enough to build a stack in terms of software, but now you're having to think about all these other things, including ground controlled, remote controlled, central command center, for example. So there's a lot, but let's really try and understand the current status quo in terms of what are some of the limitations with the current aviation ecosystem as well as the existing infrastructure.
Yeah, sure. No, that's a great point. I think it's an area that deserves, continued attention and focus as the industry matures. But living, we're headquarters here in Bozeman, Montana, and being in Bozeman, you start to understand there are a lot of airports in the country, and they're in very rural areas. They can serve a lot of needs, but they're very basic in terms of, say, their landing navigation infrastructure. Maybe they have one ILS, instrument landing system, that provides navigation, in bad weather. Most of them are untowered, or maybe they have a tower, if you're lucky, that operates just during the day, not at night. There are, those are, I think, two of the big things. And then also just in terms of radar coverage, other traffic awareness type technologies on the ground as well could be limited. And so it really kind of highlights, when a pilot steps into an airplane and flies into one of these smaller airports, how much a human brings on board the airplane in terms of its ability to navigate and operate in and out of those terminal areas. And so that lack of infrastructure and combined with, say, need for operating in all types of weather conditions is a big challenge, and probably a reason why those airports are underutilized, aside from recreational flight and a few smaller outfits.
And just for the audience to really get a grasp of this is, if you've ever traveled via car to someplace rural where there's no traffic lights, really no lights at all, and maybe you don't even have the moon, you're kind of like blindly driving into kind of this pitch dark place. And on an airplane, it's even worse, right? Because you don't really have any supporting infrastructure whatsoever, and it's really up to you to properly land safely, whether it's in inclement weather or not. So that is incredibly dangerous. And when we think about that, I think some people would naturally go down the path of, well, why don't we upgrade the infrastructure? Why don't we have manned towers? Why don't we have around the clock support? But then now you're starting to get into CapEx and OpEx. You're trying to solve this problem in a different way. So I wonder if you could reintroduce Volair a little bit more in detail, and what exactly you're trying to solve.
Yeah, sure. So, with Volair, we're developing what we call intelligent flight technologies, and that's to empower this advanced aerial mobility market, and really the scale out of these new aerial transportation modalities, and addressing some of those core challenges. So the first thing is, just a lack of trained pilots. The forecasted pilot supply compared to kind of the forecasted growth of aerial aircraft in operations has a significant mismatch. And then the other aspect is, as you mentioned, accessing either new landing environments or terminal environments, or even existing ones that lack the infrastructure. And so the technology that we're developing really is aimed at putting a lot of technology on the aircraft, similar to a human, well-trained human pilot, and their ability to make decisions about the planning and the execution of the flight, the perception tasks. So a lot of a pilot's task, especially in these these more regional airports with less infrastructure, involves a lot of navigating and perceiving the environment, visually, looking out the window for traffic. You also mentioned this challenge of landing. A lot of times the infrastructure can get you within a few hundred feet to 1,000 feet of the ground, and the pilot has to navigate, line up with the runway, flying in an appropriate glide slope, make sure that the runway is clear. Doing so in an environment where there may be other aircraft and operators that are not necessarily even communicating over a radio to announce their position. ADS-B, which is like a kind of a broadcast of an aircraft's position, does not be required. So providing the onboard systems to perceive the environment in the way a human does, and make predictions as well about the future state of that environment. And I think that's a key aspect of the work we're doing as well. Is one thing to perceive other aircraft and to be evasive. But when you start talking about operating at untowered airports, the way it works today is pilots communicate with each other, and they coordinate using kind of some, standard rights of way and standard procedures for operating at airports to be able to all integrate and leverage that airport infrastructure. So again, without the CapEx and OpEx of adding control towers and adding other systems at the aircraft or at the airport, the aircraft technology on board will need to be able to function in that predictive way as well. So those are some different, technologies that we're developing, and we're doing so on top of a foundation of data and simulation as being two essential components to developing that technology, but then also, proving out its performance across the operational landscape of all these airports and different operational modes that the AAM market is targeting.
So I want to break this up into two specific components. One is just the autonomy of the vehicle itself, but then the other piece of it is this logistical software, let's call it almost like an ERP that orchestrates between the different pilots as well as autonomous mobility vehicles. So in the case of the vehicle itself, we're talking about different types of vehicles, first of all, and they may not necessarily be the kind of typical regional airplanes, but more like eVTOLs, and the landing and takeoff is going to be fundamentally different. And so the risk factor is also going to be different as well. But talk about this notion of sight as well as seeing and sensing. And of course, there's a lot of limitations around LiDARs and traditional radars and cameras when it comes to inclement weather, fog, heavy rain, dust, whatever. It's kind of like flying in the blind, so to speak. So I wonder, what advancements are you seeing that's going to help for those vehicles to see even in the worst situations?
Sure. So I think there's probably a couple different technology paths that are targeting this particular challenge of navigating your aircraft. So where is the aircraft in the world? Making sure you don't have controlled flight into terrain, for example. There's kind of a navigational aspect where perception of the environment can facilitate that task. And then also just perception of other actors, whether they're cooperative, meaning other aircraft that are playing by the same rules as the ego aircraft, or it could be birds or other kind of rogue actors in the environment that you need to also avoid. So one of those paths, is a little bit more of kind of a infrastructural layer. So starting, in the early stages or early era of aviation, you had radar technologies and human air traffic controllers that could provide situational awareness to pilots over, a data or voice communication. That's kind of segued into an ADS-B and other similar systems that provide a more signal-based information about where are known aircraft and actors in the environment. Of course, those non-cooperative aircraft certainly are not broadcasting, and in a lot of more regional areas outside of controlled airspace, they're not even required to. So that brings it kind of to these other areas. You mentioned cameras and LiDARs and radars. How do you bring in these technologies to be able to perceive the environment and all of the different modalities that you need? Probably the easiest for the listeners to understand are cameras. We've seen a lot of advancements in not just sensing technology, from a hardware standpoint, but also from the software standpoint, being able to do facial recognition. I'm just giving an example, but those types of technologies applied, to the aviation space. We've seen several different players successfully able to detect small drones and large aircraft using cameras. But cameras have limitations. They operate differently at night than they do during the day. If you get into even the smallest amount of visible moisture, clouds, fogs, and things like that, there's challenges. And so, I think there's no one sensor that's going to solve them all. Radar is a great sensor that's been used on aircraft platforms for a long time. Is great for the in-air object detection because you have, metal shiny objects that you can reflect off and see through visible moisture and clouds. Radar is a different game on the ground where you have a lot more buildings and other infrastructure elements to impact. And then LiDAR, I think, is maybe an underexplored technology for aircraft. We've all seen the LiDAR, kind of back and forth in the autonomous driving sector, or whether or not that's essential for autonomous cars. One of the challenges is they're expensive. But when you talk about aircraft, we're talking about an order of magnitude different expense and also operational life than an aircraft. So a more expensive sensor, purpose built for a particular function, may make more sense there. LiDAR can also be, very effective long range, as well as more on the ground in the terminal area and the ground operations. So those are the types of sensor technologies that we're looking at to be able to solve this challenge that you mentioned. surrounding the perception of the environment, both in visual conditions as well as instrument meteorological conditions. And I would say maybe just as a closing point, I mentioned simulation. We think a key component to studying and understanding and advancing this perception task is through the use of very realistic and high quality simulations, going beyond just visual or graphical simulation, but being able to simulate some of the other modalities, radar, LiDAR as well, and studying the problem in that context.
Super great. Thank you for that. And we'll see if we have time to go back to the simulation a little bit more. Can you address the other piece, which is once you have a certain ubiquity of some of these autonomous urban vehicles, you're going to need a centralized way to orchestrate this. Perhaps maybe it's vehicle to vehicle, but realistically, you need to have a command center at some place, maybe at the regional, but maybe it's more on a more geographic basis that's overseeing maybe hundreds of different towers, for instance.
Mm-hmm.
How would your software first of all handle something of that nature in terms of the orchestration of it as a substitute for manned towers, for instance? Or is that an area that maybe you'll support, but maybe will support much later in the roadmap after some of the initial stack that you guys are building?
Yeah, that's a great question. And it's a very important challenge, I think, for this space, especially when you talk about eVTOL aircraft in urban environments. I think the big sky theory, which is this idea that the sky is so big, given the number of aircraft typically in the air, the odds of having a conflict are pretty small to begin with. That theory starts to erode. But as far as our focus in kind of the near term is more on developing technologies that fit into the existing infrastructure that exists today. And that coordination you're talking about is through, air traffic controllers. And in some environments, you have those all the way through the ground operation, and in others, they're only for the en route phase. That said, there's a lot of development and standards and regulatory aspects that are progressing in kind of this more coordinated vehicle to vehicle unmanned traffic management topic. And so I think as there's more clarity and kind of more capabilities in just kind of the industry in those areas, that will be kind of further down our roadmap, an area that we focus in as well.
Yeah, that makes sense perfectly. So going back to the data simulation and sensing, I think this is really the heart of your IP, I would imagine. If you could go into a little bit more depth that you could share publicly, and also as there are going to be new variety, heterogeneous sets of flying vehicles, from drones to taxis to who knows what, and all different forms of from energy, as well as battery to hydrogen, hybrids and whatnot. How will you actually support both the hardware but also the software through these simulations?
Yeah, it's a great question. So one approach that we're really doubling down on is to develop these technologies in a vehicle agnostic way. And so how that ties into simulation is that your simulation environment needs to be flexible and capable enough to study different types of operations. So maybe it's eVTOL, where you have these vertical takeoff and landings, or maybe eSTOL type operations where you're having a very short field, very steep approach to landing, all the way through conventional operations you have today. And so in doing so, the simulation environment, when I talk about data, needs to be able to pull in the infrastructural data. Think of it like your Google Maps or something, an understanding of the aviation context in a digital manner that provides kind of this kind of foundational fabric for all of this operation. And that needs to be extensible as new operations are kind of refined from the different aircraft and operator developers. And then on the sensing side, we've seen some great new progress out of companies for even flight simulators and other graphical rendering capabilities. But you need to kind of dig in a little bit further when you start being able to emulate different sensors like radar and LiDAR? What are the terrain and what are some of the data sources important there? And then also other infrastructural components like a VOR, for example, that's providing a radio beacon navigation that still may be relevant. ADS-B, being able to in the simulation environment broadcast aircraft position in a realistic manner with all of the potential faults or shortcomings of what you might see in real life of those signal integrities. And so that's, kind of all done in a very extensible way. And then finally, on the hardware piece, there's going to be an evolving hardware landscape of different sensors, and the simulation should be flexible enough to be able to inform actually what kinds of sensors and what does the sensor need in terms of field of view and other aspects, to be able to to actually refine those design requirements for the hardware. And so understanding really the core physics of those different sensors, radar, LiDAR, and things like that, so that you can actually emulate a hardware and design characteristic of that hardware that perhaps the hardware doesn't actually exist yet.
And just to be clear, for those that are listening, every one of the pieces that you're articulating really requires a tremendous amount of work. Some of which, there's a baseline of work that exists in the industry, but really there's new data set and new data that needs to be generated and optimized as well. It's a pretty arduous and really a big task ahead to be said. Now there are a number of still open challenges from the different modalities, but also you mentioned the different types of signal processing and the inputs, for example. But you have other things that's unique to flight as well. The FAA, the whole process of getting certified, both from a software, but also these physical, vehicles as well. And then the actual interaction between the pilots, because while some of these, conceivably could be autonomous, they could be also co-piloted in some sense as well. So there's a number of things. And then, of course, one of the big discussion these days is the physical infrastructure. So where would they land? Do they need to share a space with helipads, for example? Do they need new infrastructure that needs to land? Are regional airports enough? And so forth. And I think there's even a joint venture or partnership that's been announced between a domestic air carrier and electric plane, a fleet that's going to provide more of home to regionals in terms of transit, for instance. So there's a lot of open issues, and I wonder, where are we in terms of readiness, and what are some of the biggest issues that you see ahead?
Yeah, no, it's a great question. I think that for some of the more conventional flight operations, like say regional cargo, and there's several companies pursuing that. I think if you can develop advanced pilot assist technologies all the way through autonomy with perhaps a ground operation, I think that there's those to me feel like those are the closer type of deployments of these technologies that we see. But as you get further into new operations with new aircraft that maybe themselves have only a prototype, I think that's where there's kind of the slate's a little bit clearer, and there's an opportunity to develop more technology. But because of that, and there's new flight rules and new modes of operation, there's also maybe a lacking of an existing understanding of how that operation should look and what technology should support it. So I do think that there's definitely a progression. You mentioned pilot assist technologies. If you were to develop something akin to like an Autoland, Cat 3 Autoland system that could work at an airport without the over $1 million installation of that navigation system, but it looks and feels and operates very similar to a pilot as if you were operating at one of those 10 or so airports that has say a Cat 3 ILS or GLS at it. I think that there's also a penetration point there that's in the nearer term.
Super. So for my final question is that this is kind of an uncharted territory, really. And I wonder, in that context, especially you as a startup founder, how should you approach failure, especially in the context of what we talked about at the very beginning, which is really, you can't afford to have mistakes. And fortunately for commercial airlines, they've done a great job of certifying and making sure there's a high degree of safety and incredible track record on that. But as all these new developments come about, how do we ensure that level of safety continue, yet still have the opportunity for faster innovation?
No, I think that's a great question, and I really lean on my experience at Boeing, I think, to inform how we set ourselves down a path that tries to minimize the amount of failure and setbacks, and I'm not talking necessarily in terms of crashes or loss of hull or human life, but even just large setbacks in your development because of maybe you're rushing to get to a particular demonstration point. Obviously, the impact of the 737 MAX grounding on the entire industry, as well as Boeing, was a huge impact when I worked there, and understanding, to listen, obviously to the technology, the analysis, and make sure you're very conscientious of what you're doing there. But then also when I was at Boeing doing actual autonomous flight technology, the rigor behind the flight test and understanding, flight test readiness, technology readiness, kind of what that bar is, I think are also very critical things to keep in mind. And those have actually motivated us to really double down on the simulation approach. Flying is serious business, especially when you're flying prototype aircraft or prototype technologies, and simulation can get you so far in really understanding what technology needs to be built, how does it need to be built, how does it need to be tested, flushing out all of those different types of technology bugs and gotchas, both in an economical manner. It's much cheaper than flying a prototype technology, but it also can ensure that you're going out and putting technology on an aircraft at whatever stage of your development in a way that you ensure its rigor, and you can have a successful outcome of that test.
Tremendous response and spot on. And with that, I've been joined by Dr. Eric Muir, founder of Volair. Thank you for joining today.
Yeah, thanks so much for having me.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.